This is our final tutorial on Thevenin Equivalents. I dedicate this lecture to the memory of Professor Moises Szponka, an academician, a scientist, a researcher, and an engineer who shared his knowledge, his wisdom, his kindness with us, the younger generation. This tutorial is about the Thevenin-Helmholtz theorem, a theorem that was discovered by the German researcher Hermann von Helmholtz and 3 years later rediscovered and applied by the French engineer Léon Charles Thévenin. Before we begin, let's have a review of the theory seen in class. What is a port? Any pair of terminals into a network is a port. We can connect another device at that port. For instance, that pair of terminals define a port into the power utility network of our town. A network that has n nodes, and I'm counting both true nodes plus binary nodes. That network has a possible maximum number of ports given by the combination of n choose 2. Thevenin's theorem was stated related to a specific electric network at a specific port. At a port, any combination of resistors, voltage sources, and current sources, both independent and controlled ones, is equivalent to a voltage source Vth in series with a resistor Rth. We call those the Thevenin voltage and the Thevenin resistance. Well, that equivalent circuit is so only seeing the original network from outside through that port. Let's take this example. This network has nodes 1, 2, 3, and 0, true nodes, and a binary node up here. The terminals have been extended this way. How many possible ports we have? Well, combination of 5 choose 2, that is 10 possible ports. Which ones these ones? The port 01 or 02, etc. 2B, 3B. We have 10 possible ports. Given a network and the port, find the Thevenin equivalent on that port. The thing is, the same network has different Thevenin equivalents depending on which port we're looking the network through. Let's say we have port 13 in the previous figure, and we find the Thevenin equivalent for the network through that port, and it's that one. Well, that is equivalent to that network only for an external observer connected to that port, like this one. The Thevenin's theorem implies some challenge for us. We were told that we can represent any network at a given port by a series Vth and Rth pair. But how do we find those Thevenin voltage and Thevenin resistance? How? Well, traditionally, we use the open circuit and short circuit test. We find the open circuit voltage, and then we find the short circuit current, and from there we determine Vth and Rth. We've already presented them in class, being classic and all that, but I warned you also that first, in my experience, they confuse many students when they need to find the short circuit current in specific, very peculiar circuits, and the same can be said about finding the open circuit voltage. To top that, that method does not guarantee a solution. That's why we introduced another method at UBC. But even through that general method that works for any network, there are cases, 2 cases, in which we can use simplified methods. Let's see. If we have a circuit that has both independent sources and controlled sources at the same time, that is round sources and rhomboid sources, we use the 1 amp to amp method. But if we have only independent sources, only round sources, we will use a simplified method that I will describe momentarily. Or if we have only controlled sources, only dependent sources, sources with that rhomboid shape, in that case we have an even simpler method of finding Vth and Rth. Before we move on, let's define what it means to kill a source, because sometimes we will need to do that. To kill a source is to make its value 0. For instance, if you need to kill a voltage source, like this one, 10 volts, what you do is you replace its value by 0 volts. Now this source is guaranteeing that no matter what, there will be 0 volts of difference between node M and node N. Isn't there a cheaper and simpler device that guarantees the same thing? Sure is. A cable, a wire, an ideal conductor between M and N will do exactly the same job. So we say, to kill a voltage source, replace that voltage source with a wire. But we don't say it with that word. We use a fancier word. We use jargon. We call that wire a short circuit. We say, to kill a voltage source, replace it with a short circuit between the original nodes M and N. And how do we kill a current source? Well, let's take that one, 10 amps. We just make that a 0 amp current source. But a 0 amp current source is guaranteeing that no matter what, the current through that branch is going to be 0. Isn't there a cheaper way of assuring the same result? Of course there is. A pair of scissors cut that wire like so, and there's not going to be any current flowing through that. So to kill a current source, just replace that current source by an open circuit. On paper, what we do is we just erase the source and leave a hole in its path. And by the way, we also remove all the branch that current source is in. After all, there will be no current in the entire branch. The 1 amp to amp UBC method works in any circuit. There are no restrictions for its use. It works with circuits that have independent sources and control sources, on circuits that have only round sources, or on circuits that have only square rhomboid sources. But in the last two cases, we will see simplified and faster methods. It doesn't mean that you cannot use 1 amp to amp for any circuit. No, it doesn't. But if the circuit is one of these two types, you can achieve the same result much easier and faster. Observe that you can use any two values for the current sources, not only 1 amp to amp. But in that case, you have to modify the KVL equations that result. One favorite pair is 0 amp, 1 amp. But that is another story. Consider that Thevenin equivalent circuit. If we apply a 1 amp current source, a voltage V1A appears at that port. That current is producing a voltage drop in the Thevenin resistor with that polarity and that value, 1 amp times our Thevenin, whatever our Thevenin is. We can write a KVL equation in that loop like so, going up by Vthevenin, going up by 1 R Thevenin, and going down by V1A. The voltage on the port with a 1 amp current source. This value we will obtain solving the original circuit, now the Thevenin one, which we don't know, with a 1 amp current source connected to the port. From that solution we have V1A, so V1A is a known value. We move it to the right. We have one equation, but two unknowns. We need another one. Easy. We repeat the test with a 2 amp current source, a voltage V at the 2 amp source appears here. That current produces a voltage drop with the same polarity but twice as big in that resistor. We write a KVL equation in that loop, this one. And again, V2A is obtained from the actual circuit. We connect a 2 amp current source to the port of the actual circuit, solve for V2A, and then we move that V2A to the other side, and we have a set of 2 equations and 2 unknowns, Vth and Rth. V1A and V2A are known quantities. We obtain them from the M&A solution of the network with the 1 amp and the 2 amp current sources. Sometimes the student chooses, for some strange reason, to draw that current source upside down. Observe that in my set of equations I have drawn that current source entering the positive terminal, or should I say the assumed positive terminal of the Thevenin voltage. But if somehow you decide to flip it around like so, the voltage drop polarity in this resistor will change, so that means that this term will now be negative, and negative will be the coefficients for our Thevenin in those 2 equations. So you flip this current source upside down, the price you pay is you have to use negative coefficients in here and in there. Instead of 1, 1, 1, 2, you have 1, negative 1, 1, negative 2. And also, if you choose to change the polarity to V1A, like upside down, negative at the top, positive at the bottom, then those 2 signs will be positive here and will be negative in this one. Me, I prefer to leave my equations like that. Current entering the assumed positive terminals of Thevenin and the polarity of the measured voltage V1A and V2A like that. Now, how do we find Thevenin and Thevenin? If the circuit has no controlled sources, that is, we have only independent sources, in that case we kill all the sources, and we know how to do that, and the equivalent resistance that we read at the port is directly the Thevenin resistance, or Thevenin. Once we do that, we apply a 1 amp source at the port, find V1A, and Vthevenin is just V1A minus Rthevenin. If the circuit has only controlled sources, then we know something. We know that Vthevenin is always 0. No need to compute it. On Rthevenin, we obtain from a 1 amp source. Same deal, we apply a 1 amp current source to the port, and the voltage V1A that appears at the port is directly the value of Rthevenin. It cannot be simpler than that. In the general case where we have both independent sources and control sources, in that case, other people uses the open circuit and short circuit voltage, and we've spoken about that. Here at UBC, we use the 1 amp test to obtain V1A, V2A test, the 2 amp test to obtain V2A, and then we solve that system of equations. But remember that the current sources are pointed entering into the assumed positive terminals of the VTH source. Let's have a look at the 1 amp, 2 amp method. It works for any of the 3 types of networks. That's right. This is the generic case. But it's faster to use simpler methods for networks without control sources or networks without independent sources. Just a little comment: in circuits where current sources have values in milliamps and all resistors are given in kiloohms, you can use 1 milliamp and 2 milliamp tests, but when you solve, you need to use these equations then. It's 1 milliamp multiplying Rthevenin and 2 milliamps multiplying Rthevenin in the second equation. I like these values in cases like the ones described because then I can leave with only the 4 or 5 most significant digits at every point in my calculation. I'm repeating, if you flip the current sources, you need to change the sign of those two coefficients. If you flip the polarity of V1a and V2a, you need to change the sign of V1a and V2a before you plug them into this equation. If you flip them both, well, you do that for both this column and that column. I prefer to use this simpler equation, so that's why my current sources are pointed the way they are, and V1a and V2a have the polarity I showed you in class. An alternative is the 0 amps 1 amp test. Yes, you connect a 0 amp test, you write your equations and you solve for V 0 amps, and then you apply 1 amp test and you determine the V1 amp. Observe the system of equations. Notice that Vthevenin is directly V 0 amps. V 0 amps is both the open circuit voltage and Vthevenin. But the advantage is that we have the same topology to solve both for this test and for the one at the bottom. The 0 amp test is the open circuit test in disguise, but you get to keep the same set of equations for the 1 amp test. Let's work on this circuit. Generic case, case 1, we have both independent sources and control sources. We want to find the Thevenin at port PQ. What do? Well, we apply the 1 amp current source. 1 amp, a voltage V1a appears without polarity, we're assuming. How do we find V1a? Well, M&A, reference node, node 1, node 2, the currents in every branch, and then we write all the M&A equations. We solve them, and we find V2, this voltage, which is V1a, to be 39 over 7 volts. That is V1a 39 over 7 volts. That is the 1 amp test. Next, we're going to replace that source with a 2 amp current source. A voltage V2a will appear, and we need to find it. We use M&A again. Reference node, node 1 and 2. Branch currents, equations. Observe that this set of equations is exactly the same one as for the 1 amp test, but I have replaced 1 by 2. So if you're solving that set using a calculator, you store that set and then edit that to change the 1 by 2 and ask the calculator to solve it again. The solution for V2 in this case, which is this one, is 185 over 28 volts, and that is the same V2a. Now we have V1a and V2a. We solve those two equations. We have V1a and V2a. We use those values. V1a is 39 over 7, V2a is 185 over 28. We solve them. We have Vthevenin is 117 over 28 volts, and our Thevenin is 39 over 28 ohms. In an exam, please use floating point answers. That way the markers has an easier time grading your paper. This is the circuit. Always when you find a Thevenin equivalent, you need to draw it. Do not stop at just finding the values Vth and Rth. You need to draw that and identify the two terminals of the port so that the TA knows exactly that you really know what you mean. Wait a minute. How did you solve this set of equations? Well, with a calculator, you see I entered V1a and V2a and the matrix 1, 1, 1, 2. I said divide, and I got Vthevenin 117 over 28 volts and our Thevenin 39 over 28. And if I want that in floating point, give me that in floating point. This is Vthevenin 418 volts and this is our Thevenin 139 ohms. I write it down here, and that is the equivalent circuit of the original one at the port PQ. Well, you say, but wait a minute, before, how did you solve the M&A equations? All those equations? Same way. I entered them in the calculator like so. Specified what unknowns I wanted, Vx, V1, and V2. Pack! And there's the answer. V2 is 39 over 7. which is this V1A. I did the same for this 2 amp test. I just edited the set of equations, changed 1 amp for 2 amps, and asked the calculator to solve the modified system. Now let's see a simplified case. A case where we have only round sources, only independent sources. In that case, to find our Thevenin, we kill the sources. This is an open circuit, and all the branch will disappear. Open circuit, all the branch disappears, while the V source here becomes a short circuit. Now our Thevenin is equal to the equivalent resistance between nodes P and Q. That is 3 ohms in parallel with 3 plus 2. Our Thevenin is 3 ohms in parallel with 3 plus 2. That is 15/8 of an ohm. Once we have that, we find the need for VTH. How? 1 amp. We apply a 1 amp current source to the port, and a voltage V1A will appear. We need to compute it. How? M&A, reference nodes 1 and 2, branch currents, equations, solve them, and we find V2. This voltage, which is V1A, is 51/4 volts. But Vthevenin, in this case where we have only independent sources, only round sources, Vthevenin is V1A minus the value of our Thevenin. That is approximately 10.88 volts. That is, that circuit, the original one, is equivalent to this Thevenin circuit. 1088 volts and 1.875 ohms. That equivalence is only at that port PQ. That is a very nice method, right? Kill the sources to find our Thevenin, then a 1 amp test to find Vthevenin. It's really nice. However, that method works only if there is no control source in the circuit. Don't go killing sources if there are any control sources in the circuit, okay? Now, the third case, we have only controlled sources in the circuit. In this case, always Vthevenin is 0. This is the easiest of all cases. We only need to compute our Thevenin. Don't kill any source. What you do is you apply a 1 amp current source and find V1A the same way as before. And guess what? Our Thevenin has the value of V1A. There is your circuit. It has only controlled sources. So we know that Vthevenin is 0. And to find our Thevenin, we connect a 1 amp current source and compute the value of V1A. How? M&A, reference node, nodes 1 and 2, branch currents. Those are the M&A equations. We solve them and we get V2, 39/32 volts. That is also V1A, but that is also the value of our Thevenin. 1.219 ohms. And Vthevenin, it is 0. A network that has only control sources is equivalent to a resistor, no voltage source. Let's work on an exercise from the homework. In the circuit below, find what is the voltage V0, this voltage here, in the 4 kilo ohm resistor at the bottom right. Also, find its power. What should be the value in this resistor if it's to absorb maximum power? What would that power be, that maximum power? Let's have a look at that circuit. This one. We have a situation of a main actor, the 4 kilo ohm resistor, and his stage, the stage of that actor. All of that's the stage. We want to see what is the performance of that actor, the 4 kilo ohm resistor. So we replace the complicated stage with the Thevenin equivalent. We want to find the Thevenin equivalent of the set behind this 4 kilo ohm resistor. Remove the 4 kilo ohm resistor and you leave a gap, a port. We want to find the Thevenin equivalent of that circuit at that port. That is going to be the set behind the 4 kilo ohm resistor, the port PQ at which we want to find the Thevenin equivalent of the rest of the network. How do we proceed? The 1 amp 2 amp method. Apply a 1 amp current source there. In that case, I'm going to use the 1 milliamp, 2 milliamp. Why? Because the current sources here are given in milliamps and the resistors in kilo ohms. So that way I have a value of current that is in the vicinity of what's already in the circuit. I apply a 1 milliamp current source and try to compute this V1A voltage. How M&A? Reference node and node definitions, branch currents, and I write my M&A equations, which are those. You're welcome to pause the video and check them for correctness. We solve that circuit and the only value we really want is V3. V3 will be directly V1A, the voltage that appears at the port when I apply a 1 milliamp current source. That value turns out to be 41 volts. That is V1A. We repeat that test with a 2 milliamp current source in here, and now a voltage that appears is V2A or V2 milliamps. Solve the circuit again, but we don't have to rewrite the equations. We know that the only change in all the set of equations is that instead of having 1 milliamp here, we will have 2 milliamps, like so. 2 milliamps. If you have those equations on the calculator, just edit them, change the 142 and ask for a solution, and the solution is V3 again is in this case V2A 46 volts. We have V1A and V2A 41 and 46 volts. Let's find Vthevenin and Rthevenin. We write the set of equations for 1 milliamp and 2 milliamps. V1A and V2A are known, 41 and 46 volts correspondingly. Solve and find Vthevenin is 36 volts and Rthevenin is 5 kilo ohms. That is the stage behind our actor, our 4 kilo ohm resistor. Now, bring back the resistor. Yes, bring back the resistor to the stage, but replace the stage by the Thevenin equivalent like so. This is the rest of the circuit, and here is our main actor, the 4 kilo ohm resistor. Now it is very easy to find currents, voltages, and power in that 4 kilo ohm resistor. Let's do that. That voltage there is given by a voltage divider, 36 times 4 kilo ohms divided by 4 plus 5. That is 16 volts. And the power? Well, the power is V squared over R. 16 squared divided by 4,000 ohms, that is 64 milliwatts. Is that the maximum power? No, you and I know it isn't, because to absorb maximum power at that port, this resistor's value should have been the same as the absolute value of the Thevenin resistance, that is 5 kilo ohms in this case, and it isn't, so this power is not maximum. Let's compute the maximum power that we can take out of that original circuit. How? Replace the 4 kilo ohm resistor by a 5 kilo ohm resistor, as we've seen in class. In that case, we do the computations again. In here, the output voltage in this case is half Vthevenin, 18 volts, and the power 18 squared divided by 5,000 ohms, that is 64.8 milliwatts. That is the maximum power we can extract of the original circuit from that port, and that happens when we connect there, instead of the 4 kilo ohm resistor, a 5 kilo ohm resistor. Observe the difference is not that big. It's what? 1.5% difference. However, there is some difference there. Before we leave, let's turn our attention to the Norton theorem. That theorem is known in Europe as the Norton-Mayer theorem, which is an extension of Thevenin theorem. It was discovered independently in America and the United States by Edward Laurie Norton of Bell's Labs, and in Germany by Hans Ferdinand Mayer. The Norton-Mayer equivalent states that any network that has resistors and sources can be simplified and represented from a given port PQ by a current source in parallel with a resistor. Our task is going to be to find those current and resistances, the Norton current and the Norton resistance. How? First, an open circuit test. We find the open circuit voltage in this port, and that voltage is going to be directly IN times Rn. Of course, there is nothing connected here. That current is going to be flowing in that loop. The current in the resistor will flow from the top. IN amps, Rn times Rn is a voltage according to Ohm's law. That is the open circuit voltage. One equation, two unknowns IN and IN. How do we find another equation? Short circuit. Short circuit the port, and let's compute that short circuit current in this wire. How? Well, my question to you is, what is this current? The current in this resistor. And that is an R branch connected to the same node on both ends. So the voltage drop across that resistor is going to be 0. So 0 is going to be that current. But in a KCL equation here at the top tells us that all this current from the Norton source will flow through the short circuit, so the short circuit current in reality is the same Norton current. That is the result of the short circuit test. The short circuit current is a Norton current. If we put those two equations together, we find that the Norton resistance is the open circuit voltage divided by the short circuit current. And that's how we find the Norton-Mayer equivalent. You could use alternatively a 1 volt, 2 volt method. You apply a 1 volt voltage source at the port. You compute the current through it, I1 volt, and then you do the same with a 2 voltage source. After that, you write two KCL equations and solve for I Norton and R Norton. I leave that to you, my students, as an exercise. And that's the end of this final tutorial on Thevenin equivalents. Thank you very much.